Offshore oil platforms operate in some of the most unforgiving environments on Earth, requiring massive, uninterrupted electrical power just to keep their systems online and the crew safe. Enterprise data centers face a similar engineering challenge. They require mission-critical power generation, but they have to fit it into severely constrained mechanical rooms or skid spaces. The Legacy 3500 series reached its physical limits trying to meet these capacity demands. The Caterpillar C175-16 was engineered to break past that ceiling. The engine achieves this through massive physical volume. At 5.3 liters of swept volume per cylinder across a V16 configuration, the platform totals nearly 85 liters of displacement. That specific geometry delivers over 2,700 horsepower from every single cylinder. Forcing that much explosive force into a highly compact footprint generates extreme physical stress. Surviving it required a complete architectural redesign from the ground up. The foundation is the deep skirt engine block, cast from a high-tensile ferrite ductile iron alloy to prevent stress cracking under heavy, continuous loads. Inside, the geometry relies on a single central camshaft responsible for actuating 64 total valves across the entire engine. The rotating assembly paired with this block utilizes one-piece forged steel pistons and a highly specialized connecting rod design. These connecting rods are precision fractured during the manufacturing process. The rod and cap separate along a jagged crack line, creating a unique microscopic interlocking surface that can only ever mate with its original partner. A technician can never mix and match rod caps between cylinders, even temporarily during a bench rebuild. Swapping a cap destroys that fractured mating surface. Without that exact lock, the bearing shell can rotate under load, leading to total catastrophic rod failure at high speed. The mechanical foundation of the C175 offers zero margin for legacy mechanical slop or technician complacency. Turbocharging the C175 is an exercise in maximizing molecular air density. The engine breathes through cross-flow cylinder heads, a design that strictly isolates the intake and exhaust ports on opposite sides of the cylinder to optimize gas exchange. Before that pressurized air enters the intake, it passes through the separate circuit aftercooler, or SAC, which strips away the heat of compression to ensure the air remains dense with oxygen molecules. Older platforms relied on passive mechanical thermostats for cooling. The C175 utilizes an electronic coolant temperature control module. The primary engine control module sends real-time J1939 data link commands directly to this module, actively dictating exact jacket water and aftercooler temperatures based on current load. Thermal management here is an active, digitally controlled loop. Maintaining strict temperature parameters is a primary requirement for hitting the engine's power output targets. To deliver 3,500 horsepower while meeting modern emission standards, the platform abandons older mechanically actuated unit injection in favor of a high-pressure common rail fuel system. This system operates at a lethal 18,000 kilopascals, over 26,000 psi. Containing that much kinetic energy safely requires specialized double-walled fuel lines. The mechanical source of this massive pressure is the Woodward high-pressure pump, mounted directly to the front housing. The single most critical component on this pump is the fuel control valve. The fuel control valve acts as a gatekeeper. It receives a pulse-width modulated electrical signal from the ECM, constantly adjusting exactly how much of that 26,000 psi reaches the rail. From the pump, this highly regulated fuel flows out into the common rail manifolds, where it waits to be dispersed by the individual electronic injectors. The immense physical forces generated inside the block rely entirely on the fuel control valve's microscopic millisecond by millisecond digital gating. Because the fuel and thermal systems depend on continuous digital instruction, the engine requires absolute electronic redundancy to prevent catastrophic failure. Marine and petroleum applications achieve this using a dual-ECM architecture, pairing a primary control module with a secondary backup. The primary ECM continuously broadcasts its operational status, a digital heartbeat, over the CAN data link. If the secondary module detects that this heartbeat is lost or unreadable, it instantly assumes full control of the engine's functions. When troubleshooting this digital architecture, technicians must verify the regulated 5-volt and 8-volt electrical supplies feeding the active sensors. Diagnosing these circuits requires probing the wiring harness for electrical opens or shorts and trusting the active diagnostic codes rather than relying on physical intuition. Successfully repairing the C175 means shifting your diagnostic approach. You have to stop looking for traditional mechanical leaks and instead learn to read the digital data stream. Cranking an 85-liter high-speed diesel before oil has fully circulated will cause immediate catastrophic dry start damage to the bearing surfaces. To prevent this, the engine uses one of two mandatory pre-loop strategies: continuous, where oil circulates 24/7, or automotive, where cranking is physically locked out until sufficient oil pressure builds. Beyond the initial startup, how the engine is deployed, specifically in a standby versus a prime application, radically alters its long-term maintenance schedule. Standby units face infrequent, full-load bursts. They require oil and filter changes based on a strict calendar limit of 1 year or 500 hours, with valve lash checks scheduled at 2,400 hours. Prime power units run continuously. While their constant operation extends oil change intervals out to 600 hours, the continuous heat cycles double the physical wear on the valve train, pulling the valve lash check down to 1,200 hours. These schedules reflect exactly how contamination and thermal fatigue accumulate in the real world across different industries. The C175-16 generates its extreme power density through a careful balance, a highly rigid, unforgiving mechanical block paired with ultra-precise high-pressure fuel delivery. Treating this platform like an older 3500 series engine, swapping fractured rods, ignoring data links, or guessing at fuel pressures will destroy it. Mastering the C175 requires a technician who respects its microscopic physical tolerances just as much as they trust its digital architecture.